Okay, continuing on with linear independence. Okay, now we're looking at linear independence of matrix columns. And let's say if we have matrix column A, which we had to consist of the vectors going from A of 1 to A of n. For this particular matrix, the matrix equation AX equals 0 can be written as a linear combination set equal to 0, and the columns matrix A are linearly independent if and only if the equation AX equals 0 has only the trivial solution for everything we have in the weights X is equal to 0. And just to kind of give you an example, okay, we have a matrix A where we had the top row to consist of 1, 0, 1. Middle row we have 0, 1, 2, and 2, 3, 6. This will be regarded as linearly independent. And for this, okay, if I were to take what I have here, and again I have utilizing what we have with AX is equal to 0 and developing an augmented equation. Okay, so you have A, and then you have your 3 zeros with the augmented matrix performed, and okay, so we have performing the row operations and getting down to reduced echelon form. Okay, so if I take R3 minus 2R1, I have 0, 3, 4, and okay, so we have 1, 0, 0. Next pivot position is the 1 in the second row, and if I make both the top and bottom numbers 0, in this case converting the bottom 3 to 0, I have R3 minus 3R1, and we come out to 0, 0, negative 2, 0, and we have the negative 2 is in the third pivot position, and if I convert this to 1, I just take negative 1/2 of the last row. Okay, so we have with negative 1/2 of R3. Okay, and so we have just making the adjustment here. So you have negative 1/2 of R of 3. Okay, and so we have 1, 0, 1, 0, 0, 0, 1, 2, 0, and we have 0, 0, 1, 0, and then just getting to completely reduced echelon form. So you have R1 minus R3, along with R2 minus 2 times R3, and it turns out that for all of X1, X2, and X3, okay, we have to be at 0. So again, we have that this matrix is going to be linearly independent. Now, where we have linear dependence, okay, we have 1, 0, 1, 0, 1, 2, and this time instead of 2, 3, 6, I have 0, 2, 4. And if I were to perform reduced echelon form, okay, I would come out to where we have, instead of x1, x2, x3 all at 0, turns out that we have in the reduced row form that x1 equals negative x3, x of 2 equals negative 2x3, and x of 3 is free. And so in this case, again, for a matrix that does not reduce, whereupon a of x or a times x is equal to 0, where we have in this particular case, if we have a free variable, in this case x of 3, then the system is going to be linearly dependent. All right, now where we have regarding sets of 1 or 2 vectors, we have first of all a set containing only one vector. So we have S is equal to the set consisting of V of 1 is going to be linearly independent if and only if the vector is non-zero. However, if the vector is 0, then the set is linearly dependent. Okay, so just have citing a couple of cases here. So if I have a vector v1 and we have a 0 vector, well, the set consisting of this is going to be linearly dependent. If on the other hand, if I have a non-zero vector and v1 is the only vector and it consists of negative 2, 1, and 0, then the set S is going to be linearly independent. Now, in the case of what we have with 2 vectors, we have a set of 2 vectors is linearly dependent, okay, if we have one vector is going to be a multiple of the other. So we have S is linearly independent if neither vector is a multiple of the other. Okay, say if we have a couple of examples here, we have V of 1 and V of 2, and we don't have V of 1 as a multiple of V of 2 or the other way around. So this particular set is going to be linearly independent. But now in the case VO1 and VO2, if I have VO1 at 1.5, VO2 at 420, now if you notice we have for the coefficients inside the second vector, it'll be 4 times what we have in the first. And so, okay, so we have VO2 is a multiple of VO1, and this set containing both of these vectors is going to be linearly dependent. Now, for what we have for 2 vectors and more, we have for linearly dependent sets. Now we have an index set S, okay, consisting of multiple vectors of 2 or more vectors is linearly dependent if and only if at least one of the vectors is a linear combination of the others. And let's say that if you have the set to consist of where we have VO1 and VO2, whereupon VO1 is at 2.4, VO2 we have at 3.5, and if I again take 8 times x is equal to 0 and put it in vector equation terms and then forming an augmented matrix. Okay, so you have 2, 3, 0, 4, 5, 0, and then taking half of the first row, you have this stage, and then we have R2 minus 4 times the resulting first row, and we have getting closer to the reduced echelon form, so have 0, negative 1, 0 at the bottom, and then taking the opposite side of the second row, I have 0, 1, 0, and still have 1, 3/2, 0, and then putting in reduced echelon form, I can take the top row and deduct 3/2 of the second row elements, so I have 1, 0, 0, 0, 1, 0, and we have x of 1 equals x of 2 is equal to 0, and neither vector is a linear combination of the other, and okay, if it were, then we would not have a 0 vector or 0 result throughout. So in this case, the system is linearly independent. Now, let's say that as a second case, and this is taking a situation where we might have one vector to be a linear combination of the other two. And just for this case, and this was taken from one of the earlier book examples, I think it was maybe around page 28. V of 3 is a linear combination of the first 2 vectors we have given. So you have x1 v1 plus x of 2 v of 2 is equal to v of 3. And then just putting together, all right, and just writing as an augmented matrix. Okay, we have 7, 4, negative 3. Now the reduced echelon form will be 1, 0, 3, 0, 1, 2, and then 0 is at the bottom. And in this particular case, now again, v of 3 is a linear combination of v of 1 and v of 2. But let's say that if I combine all 3 vectors, and where we have a times x is equal to 0, and in this, so just combining all of these, setting equal to 0. Now again, v of 3 is the linear combination of the previous 2, and okay, so we have in the setup as an augmented matrix, have 1, 2, 7, 0, negative 2, 5, 4, 0, negative 5, 6, negative 3, 0, and following through with the following operations, we have again for the reduced echelon form, I have 1, 0, 3, 0, 0, 1, 2, 0, and you have no pivot position in the third row. So you have a bit of history to repeat, where we have x1 is equal to negative x of 3x of 3, x of 2 is equal to negative 2x of 3, and we have that x of 3 is free. And so again, in a situation where we have one of the vectors to be a linear combination of the others, you're going to have the system to be linearly dependent, again, where the resulting x is going to be non-zero, or where we have at least one free variable. All right, now just some basics here regarding 2 or more sets. If we have a set to consist of more vectors than there are entries in each vector, okay, then you're going to have the set to be linearly dependent. And so any set, okay, in R of n or Rn is linearly dependent if p is greater than n. And p is going to be in reference to the number of vectors, and will be in reference to the number of entries. And let's say that, for example, I have 1, 2, negative 4, 7, 0, 9. So you have 3 vectors, and for each vector I have 2 entries. So here we have the number of vectors is greater than the number of entries, and automatically these vectors will be regarded as linearly dependent. Now another item, and we have that if the set, very same set, or maybe not necessarily the same set, but if you had the same general set in Rn to consist of a zero vector, then you're going to have the system to be linearly dependent. Okay, so we have, for instance, you have V of 1, you have 2, 4, 6. V of 2, we have negative 1, 3, 6. And we have with V of 3, okay, have 0, 0, 0. So we have a zero vector. And because there is a zero vector, you're going to have, for this set, this will be linearly dependent.